All right, normal rain pH. 5.6. Good. And acid? Anything below. Good job. Okay. Problems associated with acid deposition, acid precipitation, or acid particles. They're going to fall on soil or fall on an aquatic biome because any particles that come down from the atmosphere are going to fall on land or fall in water. So the most affected is going to be those areas. And then, of course, plants are the ones that take in sulfur and nitrogen, so they're going to be affected. And then if you want to look at, and then the food chain, okay, if the acid is so complex. It's usually single-celled organisms like plankton and water or plants taking in the acid that are affected. So organism-wise would be them. And then structures change colors. Okay, so we're going to talk about climate, and we're going to start with what created our climate or what factors determine what our climate's like today. We're going to focus a little bit on the atmosphere and the history of temperatures in our atmosphere or on Earth, and then what changes are occurring with our climate and our temperatures. So looking at the pictures or thinking of what you know, what determines climate or what factors influence climate? Just blurt them out. Distance from the sun really is solar activity. But distance from what? You see this? What is that? No. Good try, though. Geography is one of them. Think about. Good. From the equator, but referencing the poles is good. Water circulation is more oceanic. Okay. What else? What else circulates and affects climate?
Volcanic activity.
Good job. Volcanic activity. What do we know affects climate, which is the topic we're going to talk about in this class? What are these? Humans doing what? Good. Greenhouse gases. Greenhouse gases really determine that the climate is habitable on Earth, believe it or not. And then we've got atmospheric circulation as well. So Earth's atmosphere history, we're going back 4.7 billion years. What impacted the atmosphere? The pictures will guide you. Yes, volcanic emissions. If you think of the birth of Earth, remember it formed our atmosphere, right? It produced gases such as carbon dioxide, sulfur oxides, water, forming our atmosphere. What else?
Movements of plates.
Movements of the tectonic plates, good, or the shifting of the continents as a result, which would then affect atmosphere. What else?
What's that called?
Yeah, meteors.
Oh, there you go.
What's this, guys? The sun. A flaming orange circle. No, it's the sun. And these factors led in our history of our Earth had periods of ice ages, or what they call glacial periods and interglacial periods. Some people even say that global warming is in preparation for this. That didn't happen. So I'm going to show you what Earth's atmosphere has been looking like, or temperatures in Earth have been looking like over the past 100 years. If I give you this graph on a test, tell me what you would say about this graph right here. I'll make it bigger so you could see. This was 100,000 years ago. What does it look like? What?
It goes up and down.
It's fluctuating. And by up and down, you have periods of warming, periods of cooling, periods of warming, periods of cooling. But overall, it doesn't matter where you are at what point in Earth. If I go across, I'm kind of stable up until right here, but then it dropped again, right? Peaked again. Okay. But if you go here, here, or here, which is more towards current time, we see the periods of fluctuation up and down, because if I was going to describe Earth's temperature over time, it's fluctuating up and down. But look what's happened from 1950s to 2000. We had a serious jump. There's still a fluctuation, but overall, if you look at the dotted line anywhere, we passed it. I'm going to show you a graph after from 2000 to 2020, and you'll see that continuous pattern. So how did they come up with this data? How do they know that Earth's temperature was what it was 100,000 years ago or whatever? Give me some answers. What do they use? Fossils. What else? Good. Glaciers, which what they're pulling there, and if you look really closely at the picture, they're pulling like an ice core out of the glacier. And what they're doing is taking samples of compounds, really. And then we look at organisms. What organism is this?
Plankton.
Plankton. What else?
Bugs.
Bugs are insects and what's this? Guano. I got that answer today too. Dung, droppings, right? Yes, and I got that too. Deja vu. And then we actually look at recorded temperatures. So let's say you doubt all these three things, right? Because a lot of people do. Since 1861, we've been monitoring the temperature and recording it. And you see the periods of rising, periods of cooling, right? Everything below a certain, and then all of a sudden, Industrial Revolution, it's almost like exponential growth. So like our population, our temperatures are rising at that same rate. So everything, to go back, everything that I talked about in this slide is naturally occurring. These determine our climate. Greenhouse gases, okay, or the greenhouse effect, actually make Earth a place that we could live in. So without these gases in our atmosphere, which make up how much percent of our atmosphere?
2%.
Less than 1, okay? Because 1% of our atmosphere is argon, carbon dioxide, and then other gases, especially other greenhouse gases. They help Earth be a certain temperature that we can live in. Without greenhouse gases, Earth would be too cold to live in. That's why it says inhabitable. It would be too cold to live in. So I'm going to describe how this process occurs. That's supposed to happen naturally so that we can live on Earth. But what's become the problem? Too many. We've increased the number of gases in our atmosphere, and they're causing excess warming on Earth. So here's how it works. I'm going to do the same thing I did yesterday. I'm going to describe this diagram. I'm going to label it, and then I'm going to give you a sentence for your notes that describes the whole greenhouse effect. Okay? So, and we're going to use colors. So we're going to kind of alter this diagram. We're going to use orange for our first color. Coming down from the sun are specific rays. Let me make this a little thicker and a little darker. I meant this one. Orange rays. Okay, that is not orange, but let's pretend it's orange. Come down from the sun. What kind of rays come down from the sun? Who knows? What are they called? Good job. UV rays. So you're going to write here, UV rays come down from sun. And I'm going to change this to orange, the real orange. All right? UV rays come down from the sun.
They're reflected back.
They're reflected back out of Earth. So I want you to know some are actually absorbed. So UV rays come down and they get absorbed by Earth. But most are reflected back where? Where are we going? The atmosphere and then space. Okay? So here's my re-radiated, right? What kind of rays are these? Do you know? I changed the color. They're heat rays. Anybody know what they're called? Infrared heat rays. Reflected back. Make that red so you know it matches your red arrows. What else happens to these infrared heat rays? If you look at the diagram. So some are reflected back. What's happening to other ones?
They bounce back in.
They bounce back in. What's causing this infrared ray to bounce back to Earth?
Cloud.
What's in a cloud?
Water.
Water. Water is a greenhouse gas. So greenhouse gases, in this particular diagram, water, re-radiate infrared rays back to Earth. What's going to happen to Earth? Good. Earth warms up. That's the greenhouse effect. UV rays come down from the sun. They are somewhat absorbed by Earth. Others are reflected back into the atmosphere as infrared rays. Infrared rays that hit a greenhouse gas get re-radiated back to Earth, warming Earth. If you add more greenhouse gases to our troposphere, more warming, climate change or global warming. UV rays come down from the sun and are reflected from Earth as infrared heat rays. Greenhouse gases in the troposphere will re-radiate infrared rays back to Earth, warming Earth. So besides hydrochlorofluorocarbons and hydrofluorocarbons, which you don't have to know those sources. If you see a hydrofluorocarbon on the AP exam or in this test, it is a greenhouse gas. I'm not going to trick you. HFC of any form is a greenhouse gas because there's more of them. So is sulfur hexafluoride. Again, there's the fluoride, okay? It's not sulfur dioxide. It's sulfur hexafluoride. These are greenhouse gases that you have to know, but you don't have to know their sources or where they come from. The ones that I have covered here, we know about them, okay? We know where they come from, what they're responsible for, how they're formed, all of that. What are they? Give me some examples of greenhouse gases that you know exist.
Methane.
Methane is a greenhouse gas. Good job. What else? Keep them coming. Whoops. Well, we already said water in the last side. Whoops, that's not methane. What else? Chlorofluorocarbons, which are CFCs, which we're going to talk about Monday. What else?
Carbon dioxide.
Good job. Carbon dioxide. My number one greenhouse gas of concern. What else? We talked about this yesterday. What happens when you burn fossil fuels? What primary pollutants are emitted? Sulfur, which is not a greenhouse gas. What else? Nitrous oxide is a greenhouse gas. And the last one is ozone. So we've got carbon dioxide, methane, water, CFCs, ozone, and nitrous oxides are all greenhouse gases. You were to read your textbooks, which you would, right? Because that's highly encouraged. Your textbook only lists 3 greenhouse gases. The reason your textbook doesn't list all of these gases is because the greenhouse effect is a naturally occurring process which allows us to live on Earth. It's because of the Industrial Revolution that we've increased CO2, methane, and nitrous oxide that we have a problem called climate change and global warming, okay? You can't get rid of water vapor. You know, it's a natural cycle, but these increased gases because of these 3 main reasons have led to climate change and global warming. So what caused these gases to increase? Agriculture. Now what we're going to do here is we're going to break down what agriculture has linked to these gases. What's this? What else caused global warming? Burning fossil fuels. And the last one? What are we doing here? Deforestation. So since the Industrial Revolution, we have an increase of these due to agriculture, burning of fossil fuels, and deforestation. In agriculture, if you burn fossil fuels for tractors, fertilizer, spreading, pesticide, anything that has to do with machinery is going to produce CO2 and nitrous oxides. Fertilizer, which is used in agriculture, is packed with nitrous oxides, and cows in a rangeland will produce methane when they flatulate or release gases. If you burn fossil fuels, which is everything in the Industrial Revolution to produce electricity, to farm, to build things, whatever, carbon dioxide, nitrous oxide is emitted. If you cut down the forest, you're going to lose photosynthesis from happening because you lost trees. So CO2 will be absorbed at a slower rate. There'll be less absorption, so it'll stay in our atmosphere. And if we burn the forest, it's going to produce all organic compounds or organic matter, methane, CO2, NOx. And if you cut down the forest and leave stumps and they decompose, you're going to have emissions of CO2 and nitrous oxide. at greenhouse gases. When you burn fossil fuels, you produce carbon dioxide, nitrous oxide. Methane comes from cows. Water naturally occurring.